VIT Chennai.
Pardon?
VIT Chennai.
Chennai. Okay. Okay, so how did you find this course? Have you been following all the lectures?
Yes, ma'am. I have followed the lectures also, and then I have done an internship in IUAC New Delhi.
Okay.
So I have some interest on accelerator physics, and then I have done my project in quantum field theory. So I want to switch towards the experimental things now. So I choose this course.
Okay. Okay, so do you have any doubts or anything regarding whatever has
Yes,
been?
ma'am. Yeah, I have some doubts. So you thought about side coupled structures before
Yeah.
superconducting, right?
Yes.
So how it's mathematically been correct? Because we are just shifting two phases where the opposite phase angles to other sides, right? How we will describe it mathematically?
How we will describe it mathematically? Okay, mathematical, this thing is beyond this course. I mean, that will become little advanced. From here, what is important to know is that the modes are adjusted in such a manner, it's a pi by 2 mode. If you see it electromagnetically, it is a pi by 2 mode. And if you but the beam, so what you do is, so in a pi by 2 mode, you see every alternate cell is unexcited. Okay, so there you are actually just losing power. The field is there and power is getting dissipated, so you shift them upwards so that the beam doesn't actually see those modes. So there is the field is in the perpendicular direction, the beam doesn't see them, and so the beam will see just a pi mode. So for the beam it is a pi mode, and it will get accelerated. Mathematical description will become, I guess it's too advanced for this course, then we'll have to do an advanced course on accelerator. But maybe you can look up in Wangler and all, coupling and all is given there if you're interested.
Okay, ma'am. There is another doubt.
Yeah.
So we just talked about half wave resonators and quarter wave resonators, right? So you are simply cutting that length into half, where the wavelength is been half or quarter like that. So in that cases, the boundary condition won't be matters.
Yeah, the boundary. So you see, normally we have studied that in a cavity, normal cavity, a simple cylindrical hollow cavity, the TEM mode cannot be excited. Okay, because all fields, the transverse fields, they depend upon EX, EY, BX, and BY, or let's say ER, E theta, BR, B theta. They depend only on EZ and BZ. So in a TEM mode, both EZ and BZ go to 0. So that is why that field, so if EZ and BZ both are 0, ER, E theta, BR, B theta, all will be 0. So no field, so no TEM mode will generally not exist in a resonator. Now, quarter wave resonator or a half wave resonator, these are special type of resonators. They are coaxial cavities. So as in, there is a central rod in that. So because of which, in a coaxial sort of thing, it is able to sustain transverse TEM type of mode. Okay, so it is now the electric field and magnetic field are both transverse to the to the axis. So in a TEM, so boundary condition, obviously in any resonator it has to be satisfied. But because now the central conductor is coming into picture, the TEM mode can also be excited in the resonator. Does that clarify your doubt?
So there is also a derivation like we done before for these things also, but we skipped.
Yeah, we skipped because again that will become more advanced. So we have covered only simple things like for a simple cylindrical cavity or a simple rectangular cavity. That is maybe for an advanced course.
Okay, ma'am. And then we talked about superconductivity, right? So you said even a small temperature difference in the surface of the superconductivity will lead to some tremendous increase in temperatures. How it will? What is the thing?
See, superconductivity is a property of the material. So niobium becomes superconducting at its critical temperature is 9.2. So niobium is superconducting. Now, if there is an impurity sitting on the surface, okay, so that impurity need not be superconducting. I mean, it will not have that superconducting properties. So that is a normal conductor. So that normal conductor, it can lead to because it's an impurity and it is not superconducting there, it can lead to the neighboring areas becoming from superconducting to normal conducting, and eventually, it slowly it will quench the whole cavity. So the surface has to be very good in terms of cleanliness, also in terms of surface finish. You have to get very good mirror finish. So if you've been to IUAC, you must have seen the superconducting cavities there. They have the electropolishing setup for the preparation of the surface. They also have high pressure rinsing so that no impurities are there. So if there is if the surface finish is not good, so if there is a small let's say a small region where the surface finish is not good locally, in that region the electric field could be high. The surface electric field could be high, and that surface electric field could lead to high values, because since electric field values in the superconducting cavities, both electric field and magnetic field are very high, they could lead to surface emission, and then eventually either a field emission or a breakdown. So that is why the surface preparation has to be very good, both in terms of removal of impurities as well as surface finish.
Okay, ma'am.
Any other doubt?
No, ma'am. Super no.
Okay.
From this week, have you gone through this week's lectures? Focusing.
I finished up to superconductors, and week 6 first lectures I completed. Transverse dynamics. That's only I just completed.
So
Transverse dynamics you completed?
Yes, ma'am. Up to that lensing thing.
Okay.
So you have no doubt in that part?
Up to no, because it's under just matrix things that and all only covering, right? So I have no doubts on that.
For superconducting accelerators, you can refer to this book by Hassan Padamsi. So both part 1 and part 2, they are quite detailed and nice.
Okay.
So I don't know, could you access the reference books?
I will try.
Length is good from Haris Rauf. So I feel that the bowling...
Asal Patal Singh, right, ma'am?
Yeah, Hassan Padamsi. So
Okay.
there are a couple of books by Hassan Padamsi, RF superconductivity for accelerators, something like that. The title I have given the title in the beginning lecture, my first lecture there. So maybe you can look at
Sure.
those. Yeah.
Sure.
And you may actually have got, if you've been to IUAC, you must have got good hands-on experience. I mean, they have good facilities there, so you must have actually seen some facilities related to superconducting cavities.
Yeah, I saw them.
Yeah. Okay, so no more doubts?
Yes, ma'am. No more.
Okay, so what do we do, Rohit? Should we wait or?
Yeah, I mean, still have time. But yeah, maybe we can wait. So, ma'am, I just wanted to to discuss something. So yeah. So for this in this week, we mainly studied the focusing of the beams using different methods. So in to use the magnetic field to focus, we have two methods, like using a quadrupole, magnetic quadrupole, or we can use a solenoid. Right? But what I have seen is that most of the accelerator uses quadrupole. They don't use solenoid much. I mean, the larger accelerators.
The solenoids are also used. So okay, you can complete your question then. I will.
Yeah, like in LHC, I think only quadrupoles have been used. But what I find is, so for the quadrupoles you need you need pairs of them to focus the one. You need in a pair every time, because one focuses in one axis and defocuses in other direction. So that's why. But in solenoid we don't have such kind of problem. So why not we use solenoid? I mean, is there some mechanical problem with the solenoid or something?
So solenoid actually, if you see quadrupole focusing, it is linear focusing. The force is directly proportional to F is proportional to X.
Distance.
Whereas in a solenoid, it is a second order focusing.
Okay.
So you see that the force acts twice. First, it interacts with the radial part of the velocity, the radial part of the field, and then with the Z component of the field. So the field is, so the focusing is in general second order focusing. Okay, so so that is why generally quadrupoles are preferred. Quadrupoles are linear; they will not introduce any increase. Since they are linear, they will not there will not be any much increase in the beam emittance. Whereas solenoids, due to the second order focusing, also due to there will be aberrations because at the ends. So that is why the focusing in the solenoid could lead to some increase in emittance. Nevertheless, they have advantages that it will focus in both the directions. You'll get a round beam. With a quadrupole, if you use a pair of quadrupoles, it will give you a beam. It will give you a beam of different sizes in X and Y. Whereas a solenoid will give you the same beam, but the beam will be rotated. So there is this because inside the solenoid the beam gets rotated. So the beam will be rotated, but yeah. So because of linear properties, generally quadrupoles are preferred, but solenoids are preferred in certain regions, like like in LEIPA, we have from the ion source to the RFQ. RFQ is an accelerator, which we will see in further lectures. So there we need a round beam at the entry of the RFQ. So a solenoid is preferred there. Otherwise, you will have to use at least 6 quadrupoles for focusing there. So under special conditions, it is used. Otherwise, quadrupoles are generally preferred. So are you also following the course, Rohit?
Yeah, I'm also following the course because I'm my research work is not in, like, I'm not doing some related something to accelerators.
Yeah, I know. You're working in high energy physics,
Yeah, I'm
right?
working in experimental high energy physics, mainly physics analysis, not that much into hardwares. So yeah, so I'm also following the lectures and
Okay.
So yeah, maybe what we can do is I can stay here, and if someone comes, I can maybe I can ping you on mail.
Okay, I'll be around. I'll just switch off my video and audio, but I'll be around.
Yeah, sure.
So yeah.
Okay, yeah, sure. That we can do. And hi, Dhanush.
Hi, sir.
Yeah. So any other discussion you want to have, or anything you want to ask? We can chat maybe.
What mode of exams will be in final exams? Whether it will be pen and paper or just one mark questions?
It will be same, like MCQs will be there.
Oh, okay.
Because exams will be online, right? So.
Sorry, what?
So exams will be online, right? So it will be mostly MCQs.
Okay.
Yeah. So you have registered for the exam? You have to register.
Yeah.
Okay. Yeah. So you have finished your masters, right?
Yes, I finished my masters.
Okay. So now you are doing some project, or?
No, actually, I'm preparing from a net and gate preparation.
Okay.
At the side by side, I'm just doing this NPTEL courses also.
Okay. That's nice.
At the same time, just trying to put some paper on my final project.
Okay. So what was your project on?
It's in solitons and scalar field theory.
What? Solitons.
Yeah, solitons and scalar field theory. I used Monte Carlo simulations to get that solitons.
Okay. That's nice. So now you want to switch your area of research, right?
No, not completely. I want to switch. I just want to get into some experimental things. That's it. In MSc, I don't have that facilities in my lab as well as in my college as well as I don't have nearby. There is no place to do such things. So I get into theoretical things. Now I just want to switch to experimental.
Yeah, that's nice. So, like, what kind of experiments you want to get involved in?
So far now I'm just researching into some basic concepts on nuclear physics. I just interested in particle physics and nuclear physics most probably. That's why I just choose this course. So my basic interest was hard-run theories, and then nuclear interaction with scalar fields, like those things and all.
Yeah, those are interesting.
Which and all comes in the direct application of QFT I'm interested in.
I understand. So you have done courses in QFT and high energy physics?
Yeah, I have done courses on QFT. Now also I registered for another course on QFT. That's also having the same exam date of this course.
On NPTEL?
NPTEL only, by Anurag Tripathi.
By whom?
Anurag Tripathi, sir.
Oh.
IIT Hyderabad, I think. Yeah.
Okay. Yeah. So maybe it's because India-Pakistan match, no one is joining.
I think so.
Okay, if you want, you can leave. If you have no anything else to discuss, then you can leave. I'll wait if someone will join and have some doubt.
Okay, sure. You said that you just solved some problems in previous week section, right?
Yeah.
I have that YouTube link. Where can I find it?
What?
You recorded it and uploaded it in YouTube,
Yeah,
right?
I have uploaded it. You can find it on the NPTEL site, I guess. It will be somewhere. It will be linked.
What is the channel name? It's useful to find it.
What is the
channel name?
Channel name.
You uploaded it to YouTube, right?
Yeah, but the videos, there should be a link on the NPTEL website. If you go live sessions, there under the live sessions you can find my channel. Can you check it?
Just a minute, I will check it now itself.
If you're on the laptop, maybe you can share screen. I can guide you.
No, here it's raining, so I just joined in my phone.
Oh, okay. Then you can check. Let me know if you can find it.
Yeah, sure. No, here there is no such thing.
There's
In
no.
Accelerator Physics, there is only one tab like download videos. That's it.
Okay. Should be there. Okay. Let me then give you the my channel name. Okay, you can directly go and search for Accelerator Physics. Uh,
Or else, can you please copy paste the link in the chat box here? That will be useful.
yeah. Okay. Sure. Uh, so this is the link for the last lecture, last live session. Okay, and did you see it?
Yes, I'm going through it.
Oh, okay. Let me know if you can open it and.
Yeah, I got it.
Okay.
Sorry.
Great. Yeah, so if you want, you can go through them. So I'll start with some of the concepts. I'll recap some of the concepts of week 6, and I'll solve some example problems for this week. Here we mainly have in this week we mainly studied transverse dynamics of beam and how to focus and how to focus a diverging beam and various mathematical concepts like transfer matrix uh, and yeah, how we can mathematically see the focusing which is happening by different kind of objects like quadrupole or solenoid, things like that. Okay, so let me start with some of the basic concepts, recap some of the basic concepts. So, as I mentioned, this week we mainly have this is topic. I think this is yeah. So this week we mainly have transverse dynamics. So what happens is, suppose a beam moving in z direction with a vz velocity. Uh, there are components of velocities in the y and x direction too. Okay. I mean, this is inherent inside a beam. This is due to many effects, due to effects from the RF fields or space charge effect. Many things are there. So what we get is the the resultant component of uh, velocity is in a direction uh, which is not towards the g direction, which is favorable. And what we desire is we should have these transverse component of velocities Vx at Vy less than Vj. So this is the favorable condition, and but this is not also always true. So we have to find some method to converge the beam, to take the beam towards this direction, and this is what called focusing. So there are two ways to focus the beams: magnetic, using magnetic fields or electric fields, and magnetic fields are more effective uh, in converging a diverging beam. Uh, there are some so to see that you can clearly see. So uh, you know that the force due to a magnetic field is on a charged particle is given by F B cross B. Q is the charge of the particle, and we know that in accelerator the velocity can go up to towards close to speed of light. So let's put V equal to C, and so magnetic force will be Q, mm, not exactly equal to, but yeah, QCB. And for suppose a magnetic field of 1 Tesla, uh, force sorry force will be QC, right? And now if we have the same thing, if we use an electric field for the same charge, so what is the force due to electric field? It is QE. Okay, and suppose we want to achieve the same force using an electric field, so we just equate QE equal to QC. Okay, and you find that the electric field needed, so QQ get cancelled, and E equal to C, and you know that C is 3 into 10 to the power 8. So when you convert it into million volt, it is 300 million volt per meter. Okay, so and this is a very high electric field, and it is not possible. Okay, so that's why for a high energy beam, for a beam moving with a very relativistically high speed, we need magnetic field to focus the beam. And so the most common, uh, magnetic object that we use to focus the beam is magnetic quadrupole and also solenoid. So how so so in the case of magnetic quadrupole, uh, the in a magnetic quadrupole, the magnetic field is proportional to the uh, so the magnetic field in the y direction is proportional to the x direction, and magnetic field in the x direction is proportional to the y direction. And those are, and so we can write this like using a constant of proportionality, which is g. It is called gradient, field gradient. Okay, so and so this type of magnetic field produces a force given. So I'll just show what and what is the direction of force in the transverse direction. So in this is XY axis and Z axis is coming out of the screen. So so the force due to this kind of magnetic field will be given like this. So let me just write it something, explain. Okay, so see what this magnetic quadrupole will do is it will focus the beam in the x direction because see it is squeezing the beam in these two directions. Okay, but it will defocus the beam in in the y direction because it is the force is in the opposite direction, right? So that's why we need a pair of quadrupole to focus the beam in both directions. What we can do is we can reverse the polarity of quadrupole, and what that will do is it will uh, reverse the forces, and so we get the focusing in both directions. Okay, so magnetic quadrupole uh, are always used in pair. Okay, okay. So this is okay. Now one more thing, and the force that is produced by magnetic quadrupole is simply, so suppose we have force due to magnetic field is given by Q V cross B, and we know that uh, so suppose first let's look at the x component. So V cross V, the x component of V cross B is will be just uh, because V has only Z component, so it will be VZ Vy, and it will be, and we know that the By is given as this, so Gx. Okay, and similarly Vy is Q V cross V by component, and it will be Q uh, because we have only Vz component of velocity, so Vz and with Bx, and Bx is here G is equal to Cy, so Bx G. So we see that both the forces are proportional to I mean fx is proportional to x and fy is proportional to y. So it is a linear force. Okay, and what does this mean physically is so suppose we are using a quadrupole to focus a beam. So uh, it is very it is in favor of us because see suppose this is the beam line z axis and a particle is here at a distance suppose x, another particle is here. So this force will exert a larger force on the particle which is away more far from the beam axis than on this particle which is near the beam axis. So so this is what we want. This is so what will happen is the beam will all the particles will come close to this beam axis, and this is what we want. This is what we call focusing. So yeah, mm, it is very favorable condition for us. Okay, now to see this mathematically, have a little bit mathematics involved in this. Uh, there is a concept of trace space. Okay, so what is trace space? So trace space is a proxy for phase space, and the coordinates of trace space is x and x prime, where x is the just the coordinate, x coordinate, and x prime is the divergence of particles, which is dx by dj. Okay, and and the momentum of particle is proportional to the x prime. Uh, okay. This derivation you can find in the lectures how it is possible, and you can think about it also. It's straightforward. Okay. So yeah, we have this coordinate for trace space, and now what we can do is we can have a matrix formulation of uh, yeah, free space, and where there is no field to focus, and when there is a quadruple field, uh, what will happen to the coordinate of the particles. Okay, we can have a matrix formulation. So yeah, let's see that. So suppose we are in a drift space. Drift space means field free region. Here, so here what we have, suppose this is the beam line. This is point A to point B. Now, suppose there is a particle here, okay, and suppose this is we are talking about a length L inside the beam, right? And its coordinate is x1 and x1 prime. What will happen is in a field free region, it will diverge because it has a velocity component in the transverse axis. It will diverge like this and reach to a point x2, x2 prime. Okay. So now we can simply we can uh, we know the if we know the this this slope of this line, you can write x2 as x1 plus lx1 prime, right? Straightforward. And x2 prime will be same as x1 prime because there is no uh, there is no change in the slope, right? So whatever the slope here at point x2 is the slope at the point x1. Okay, and this we can write in a matrix form like this. So x2 prime, we can write this as 1 0 1 x1 x1 prime. Okay, and this matrix is called uh, drift space transfer matrix. I mean, this is transfer matrix in drift space denoted by NB. Okay. But now, if there is a particle in a quadrupole field, then what will happen is, let's see. Now here again, uh, there is 2 points will be there, but uh, so so there is a force on there is a force on the particle, and okay, I'm not going into detail here. I'm just recapping. So the equation of motion is this. Okay, for a single particle in a quadrupole field, we get this kind of equation of motion, and this is the harmonic. This is the equation of motion for simple harmonic oscillator, and we can write this as a kx because it's a constant for a particular domain. Okay, and so we can write this as, okay, it is equation of motion of SHM, and its solution is given like this. Sinusoidal solution plus b sine kx. Okay, uh, so and then you can differentiate it and get x prime, and also then you can apply the boundary condition, so you can take uh, quadrupole of length L. Okay, and suppose here the beam is here the particle is at x1, just focusing going to x2. Okay, it's the z direction. So when you apply the boundary condition at x1 and x2 in this solution, uh, you get this kind of matrix. So again, this has been done in the lectures in detail. You can refer that. I'm just writing out the results. So you get this kind of, and here x1, x1 prime. Okay, so this is the transfer matrix for a quadrupole. Okay, in the x direction. Similarly, you will have a matrix in y direction, which have hyperbolic functions instead of simple cos and sine. Okay, so yeah, this is mqx, and uh, you can get the expression similarly for the in the y direction. Okay, so yeah, this in this way we can see the in this way we can visualize the focusing in within a mathematical framework. Okay. And yeah, then because see, it is this quadrupole is doing is focusing the beam. We can define a kind of focal length. Okay, so what is focal length here? So focal length. So suppose this is the um, direction of the beam, and we have a quadrupole. There is a beam. There is a particle, and at x1 it enters the quadrupole field and get focused, exit the quadrupole beam, and uh, goes like this. So this this distance is what we call focal length. Okay, after it after so so think of it like a lens. So you know, in optics, if you have a converging lens and a beam coming parallel, light beam, it gets focused. In this direction we call the focal length. So similarly here also we have this direction as focal length. Okay? And so I'm not going to derive the focal length. I'm just going to write the focal length in terms of our in terms of our term variables. Okay, this is fx. So and similarly in the y direction we have hyperbolic functions. So cot h. And so here, if we have a very thin lens, okay, if L, this length of the quadrupole lens is very small than the focal length itself, so this is a condition for thin lens, then uh, this expression, so again, we can write the 1 by fx, and we have kx, we have tan cube, because cot inverse is tan, and L is there, and we can divide and multiply by uh, kxl, right? So yeah, so suppose here we, oh, here L is there, so this is and using the L hospital rule, we know that this goes to 1, okay, because L is very small, so tan theta is theta, and so theta theta equals to 1, and so we get kx, okay, and hence fx is what? Fx is simply 1 by kxl, which is, and we can write the expression of kx, uh, which we have which we found earlier. So 1 by qg. So mvg comes over. So this is the expression for focal. Okay. Next direction. and the transfer matrix for a thin lens is given by this minus plus, right? Here negative is for defocusing. Okay. And positive is for focusing. Uh, okay. So this is what we have for focal length. Now we can also see uh, for a suppose for a beam. Uh, so this is all for a single charged particle. Okay. Now if we have suppose a beam of particles moving. Okay. How do we consider that? How do we study that? Okay. So for that, uh, we should write some kind of general equation. We should have some kind of general equation of motion. So suppose we have a periodic lattice. Uh, as I mentioned, the quadrupole is not. We cannot use a single quadrupole for focusing. We have to always use a uh, pair quadrupole in pairs. So uh, suppose we have some kind of lattice like focusing, defocusing, focusing, defocusing kind of thing. Okay, and so this what will happen is this constant that we have will be a function of the longitudinal direction, and it will be periodic like this. So it will repeat after say length L, okay, and similarly in the for the y direction too, okay, and I've already written the equation of motion, which I will write it in a more generalized way. Okay, and as I mentioned here, Ks is Ks plus F. Okay, and this is called the Hill's equation. Right? And its solution is given like this. So constant and beta of S. I will tell you what beta is. Cos phi s plus phi 0. Okay, where beta is also a periodic, also periodic in S. Okay. and we can write this. So we can visualize this with this figure. Suppose this is the S direction, and this is the X. This is the X axis. This beam, the beam travels like this. So there is the envelope like this, okay, and inside it we have the motion. We have the accelerative motion like this. Okay, so this beta is the is what uh, is what gives this envelope. Okay, and we have the cost function, which gives us the cost motivation inside the envelope. Uh, I wanted to add another page here. Okay, maybe we will manage here. So yeah, so this is the general equation of motion and its solution given like this. And yeah, here the phi is given by, so for a length L we can write phi like this, and there is a parameter called alpha, which is the differential of beta by 2, and there is another parameter called gamma, which is 1 plus alpha s square by beta, and these parameters are called Swiss parameters. And if you solve the Hill's equation, you can get motion in the phase space. So again, these things are discussed in detail in the lectures. I'm just writing out the relevant things. So this is the equation in phase space. Gamma x squared plus 2 alpha x prime plus beta x prime square equal to epsilon, and this is the equation of ellipse. Okay, and here epsilon is a constant, and it is called emittance. Okay, and and this ellipse is the shape of the ellipse is determined by alpha, beta, and gamma. So called that these parameters, and the area of the ellipse is defined by this epsilon, called the emittance. Okay. So So the emittance is the for the so suppose we have a bunch of beams inside our accelerator. So every beam has its every particle has its own ellipse, and the doesn't look like this, but consider this in ellipse, and the area of the the, the epsilon of the largest uh, ellipse is called the emittance. So emittance is area by pi. So pi we divide by pi to make it understand really consistent. Okay. So yeah, I think this much of recap is fine. So let's move over to some examples and see how we can apply this concept to solve some problems. Okay. So first problem we have here is so it's a very simple problem. So the focusing due to quadrupole is linear, uh, true or false. So as I mentioned earlier, the force due to a quadrupole on a charged particle is proportional to x, and in y direction is proportional to y. So yeah, in fact it is linear force, right? So this statement is true, and okay. Then we have the second problem. Here, the question is a quadrupole magnet of 58 is operated at a gradient of 10 Tesla per meter and is used for focusing a 5 mega electron volt beam. Calculate the thin lens focal length. Okay. So this is a little bit involved problem. So what we have here is, suppose the length of the quadrupole is given 5 centimeter, and magnetic field is given 10 Tesla per meter. Magnetic field gradient, sorry, it's not magnetic, it's the magnetic field gradient G, and we have the kinetic energy of the proton beam given 5 mega electron volt, and we want the thin lens focal length. Okay, so the formula of thin focal length is, as we have seen, mvj by qgl. Okay, so we know the charge of the proton. Okay, we know the mass of the proton. uh, G is given, L is given. So we have to calculate Vj. right? The velocity of the proton beam, and we have given kinetic energy. So to get the velocity from the kinetic energy, what we can do is um, we can use this formula. So we know that relativistically kinetic energy is what? It is gamma minus 1 m naught c square, right? Because this is a relativistic kinetic energy, it's very high, right? So we have to use the relativistic formula. And so let's put everything here. So 5 into 10 to the power minus 6 eV is equal to gamma minus 1. Mass of the proton is 1.67 into 10 to the power minus 27. Speed of light is 3 into 10 to the power 8 meter per second square. So uh, if you solve this, and we know that one electron volt is 1.6 into 10 to the power minus 9 joules. So putting everything inside this formula, and you can solve for gamma, it will be around 1.03. Okay, and we know that gamma is 1 by 1 minus v square c square, and so using this you can get the v as 2.768 into 10 to the power 8. So it is very close to the speed of light. So that's why I called it is relativistic speed. Now, now we have v velocity, which is in z direction. Okay, z. Now we can calculate the yeah. Now we can calculate the focal length, which is mvj by vgm. So mass of the proton is 1.67 given to the power minus 27. Uh, Velocity of the proton is 2.768 into 10 meter per second. Then charge is 1.6 into 10 power minus 19 coulomb. Magnetic field gradient 10, and the length is given 0.05 meter. Okay. So solving this, you will get 0.627 centimeter, which is 60, meters, and this is 62.7 centimeter. So option B is correct. Okay. So this way you can prove this kind of problem. Okay, next uh, problem we have. So for a thin focusing lens, the motion of a charged particle in trace space is represented by. So here red denotes the initial coordinates and blue denotes the final coordinates. So we know that uh, for a focusing lens, uh, so what focusing lens does is, so suppose a charged particle is going like this, it will change its slope, right? So, or suppose there is a diverging particle and it will change its slope. So, and because it's a thin focusing length, the change in x is negligible. So here, here you see the x prime changes the direction from positive to negative, and with no change in x, and here the direction is opposite, so it can't be true. Okay, because this means that it is diverging, and it is also, this one also cannot be true because here the slope doesn't change at all, and here the slope changes but x is also changing, so this is not for thin lens. So yeah, this is true only for the thin lens. Okay. Now the next question: the location where the beam size is maximum in a periodic lattice, the value of this parameter alpha is. So I mentioned the beam size is given by this envelope, which is quantified by beta, okay, beta of s, and alpha is what, beta prime, right? So wherever uh, the beam size is maximum, so suppose at this point the beam size is maximum, uh, so and we know that if we differentiate something at maximum, it should be 0, right? So 0 is the correct answer. Now, next question: which of the following is independent of longitudinal coordinates? So alpha depends on the longitudinal, alpha, beta, and gamma. All the three depends on the longitudinal coordinates I just showed. The beam emittance does not depend on the longitudinal coordinates. So D is the correct answer. Beam emittance just depends on the area, right? Area of the largest ellipse, which is not a function of s. So okay, next question. Uh, for a periodic lattice, which of these are true? So the beam envelope repeats after every period. Uh, so uh, so beam envelope. Okay, so this is true, right? Beam envelope obviously repeats, but the single particle trajectory does not repeat after each period. I just saw the diagram. A second. So this is so this is one period, okay? And here the beam envelope repeats, but the charge, the single charge particle trajectories, these this does not this repeat much before or much longer, okay? But this does not repeat with the period. Neither the beam envelope nor the single particle repeats after each period. This is also not true. Both not true. So yeah, option A is correct. Okay. Okay. Next question. A large value of this parameter beta represents. So a large value of beta. So what does it mean is that so in x direction, so beta is amplitude in the x direction, right? This is beta. So the large value means that it's a larger beam, right? So C option. It does not mean divergence or convergence. It's just a larger beam size. Okay. Then next question. A quadrupole is designed to focus a proton beam of energy 100 milli-electron volt. The same quadrupole is used to focus 100 milli-electron volt neutron beam. The focal length is we just saw that the focal length is given by what uh, m bj by qgl. Okay. So for a proton, so suppose let's write for proton mass of proton and velocity of proton beam q of proton g is same l is same. Okay. And then for deuteron has twice the mass of proton Vj, but it has also it has just the half. The charge of the deuteron is same as the proton, right? Vg. So the focal length is what is happening is the focal length is increasing, right? In case of deuteron, it's twice the what we have for the proton. So the correct answer is B. Because deuteron is what? One proton plus one neutron. So charge is just the same as proton, but its mass is twice the mass of proton. Okay. Uh, then we have next question. So which of the following are true about superconducting cavities? So okay, the options are the pair of solenoids is required to focus the beam in both directions. We don't need pair of solenoids because a single solenoid is enough to focus. The focusing due to electric quadrupole is velocity dependent. We saw that the force due to electric field does not depend on the velocity, so it's not true. The focusing due to magnetic quadrupole is velocity dependent. Yeah, this is true. Uh, the pair of quadrupole is required to focus the beam in both directions. Yeah, we also saw this is also true. Moving to the next problem. Single particle behavior can be studied by. So I just mentioned we can use Hill's equation, and also Hill's equation is same as the transfer matrix method. So these two methods. Envelope equation I showed this is for a beam, and sigma matrix is also for a beam. So for single particle, A and B is true. Okay, so this is all for today.